So, welcome to lecture 2. We're going to start talking about computational Boolean algebra. Now, that's an interesting set of words. I'm assuming that everybody who's decided to take this class knows something about Boolean algebra and can do things like manipulate the equations by hand and maybe do things like Carnot maps to simplify things. But that's a far cry from being able to write a computer program that deals with something like a Boolean equation as a data structure manipulated by an operator. So in this first set of lectures on computational Boolean algebra, lecture 2.1, our first topic is how do we take complicated Boolean things apart into simpler pieces? So we're going to introduce the foundational tools for doing that.
So here's lecture 2.1. This is where we're going to start talking about Boolean algebra from a computational angle. Computational Boolean algebra basics. So what do I mean by computational Boolean algebra? Look, by way of background, I'm assuming that you've done some Boolean algebra, you've done hand manipulations of these algebraic equations, you've done Carnot maps to simplify little Boolean equations. I've got one shown on the right. But look, this is just not sufficient for real designs. And as a concrete way of just illustrating that, let's suppose that I actually told you that I have 40 variables and I'd like you to optimize it with a Carnot map. Do the math. It's got about 1 trillion squares. You could, in fact, fit that on an American-style football field, which is 100 by 50 yards, by the way. But every map in the Carnot map would be about 60 by 60 microns, so that's 60 millionths of a meter. That is just really not happening. There has just got to be a better way. So what we need is a computational approach. We need an algorithmic, computational set of strategies for Boolean stuff. We've got to be able to think of Boolean objects as data structures and operators. And that's just a really new thing. So what are we going to study? We're going to study 3 things. We're going to study decomposition strategies because the way you do something that's really complicated is by taking it apart into simpler pieces, solving what you can on the simple pieces and then putting them back together. So there's a set of advanced concepts and terms you need to be able to do this. We're also just going to look at some computational strategies, ways to think about Boolean functions that let them be manipulated by programs. That's a big thing. And then we're going to look at a couple of small but really interesting applications because when you have new tools, there's some new and interesting things to do. And I find that it's actually, and this may be a little surprising to you, it's interesting to go back to calculus as an analogy here. One of the things you probably learned somewhere in high school is that you could take complex functions, for example, something like e to the x, all right, so there's e to the x, and you could actually express e to the x as simpler pieces, right? So suppose that you have powers of x, you have 1, x, x squared, x cubed, and stuff like that. You can glue those things together and you discover that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and on you go. And that was pretty cool. And in calculus, you go a little further, we tell you there's a general formula, the Taylor series expansion, and I've got it written below. It's kind of like the e to the x expansion. It actually is that, but it's the general case, and it involves first and second and third derivatives and things of the function evaluated in an appropriate set of places. And if you take a little bit more math, you're going to find there's a whole bunch of other ways of taking complicated functions apart into simpler pieces. For example, in engineering, if it's a periodic function, you can use a Fourier series. Here's a great big new question. Is there anything like this for Boolean functions? Can I take a Boolean function apart and put it back together in simpler pieces in a way that lets me do something useful? And the answer is yes. Yes, exclamation point. It's called the Shannon expansion. It's very famous. It's so famous that it's even got its own Wikipedia page. And so this is one of the wonderful inventions of Claude Shannon, an incredibly famous individual. This is the person who invented information theory, much of the mathematical infrastructure for modern communications. This is the person who invented the word, or at least coined the word bit for binary digit. Very famous guy, our Claude. And the Shannon expansion is a very simple kind of an idea. So we're going to start by defining something new. So we're going to define a new function, which sounds a little strange. What if we take the existing function that we've got, this f of x, which is shown above, and we set one of the variables to be a constant value, right? So we've got this variable xi as a constant, and we're just going to either set the value of xi to be a 1, or we're going to set the value of xi to be a 0. That's pretty easy to do. Let's just sort of do a couple of examples. If I've got this little function f of x, y, z here, if I set x equal to 1, let's just look, what do we get? All right, so x is a 1, so I'm going to get a y, and then x is a 1, so I'm going to get a z bar, and then x is a 1, so the x bar turns into a 0, and I believe I get a y z bar. Okay, so that's the function. And I could simplify that a little bit more. If I take y equals 0 and do the same thing, okay, the first term goes away, I get a 0, and the second term I get an x z bar, and the third term just goes away, so I get x z bar. All right, so that's what I get. Now, here's something I'm going to say a whole bunch of times until you remember. It's a new function, right? But it no longer depends on this variable. Okay. Once you set xi to a constant, there are no more xi's in this function. Makes sense, right? They're constants. The variable went away. So these things are spectacularly useful, so they have a name. They're called the Shannon cofactors. Right? So it's the Shannon cofactor with respect to a variable. And there's a couple of ways you write this. If you take the function and you set the value to be a 1, all right, then the most standard way of writing this would be f of xi as a subscript, right? And that's, we refer to that as the positive cofactor, right? And if you set xi to be a 0, we refer to that as the negative cofactor. And to be honest, and I recognize it's a little bit sloppy, but everybody does it. Sometimes we're just going to write this as f of xi equals 1 or f of xi equals 0, ignoring all of the other variables, which is mathematically a little sloppy, but it's just easier to type. So that's what they are. That's what they're called. That's how we write them. Why are these useful functions to get from f? Well, the big reason is that there's a very famous theorem. It's called the Shannon expansion theorem. If I give you any function f of n variables and I pick any of its input variables xi, that function can be represented in this very simple way. The simpler pieces that you decompose the function into are the positive, there's the positive cofactor, and the negative, there's the negative cofactor. So you have xi, the variable, anded with the positive cofactor, plus or xi bar anded with the negative cofactor. So take the positive form of the variable, and it with the positive cofactor, sum in the negative form of the variable and the negative cofactor. And you can always take a function apart in just that very simple way. And it's amazingly easy to prove. Not exactly a proof, it's kind of more just like a case study. You know, let's just let xi be a 1 here. Okay, well, then what happens? So, you know, we've got the value of the function, right, which has a bunch of variables in it, but there's xi equals 1, right? And we're claiming that that's supposed to be f of 1 times the positive cofactor plus 1 bar, which is a 0, times the negative cofactor. All right, you know, that term just goes away, and this thing just turns into f of x equals 1, which I said was kind of a sloppy way of writing the cofactor. And that's true because that's just the definition of this thing. You know, there's just nothing else going on there. And if I was to say let xi equals 0, I'd just get the same kind of I'd get basically the same kind of a derivation. I'd discover that f when you let xi be 0 is equal to f when you let xi be 0. Right? So it's a very simple kind of an idea. It's a deceptively simple kind of an idea, but it's an amazingly powerful idea, and it's one that we're going to use all over the place. Here's just another way of viewing what the Shannon expansion is and what it does. And I'll just remind you of what a mux is. Right? This is a multiplexer. Right? So a multiplexer is just a little piece of hardware. Right? It's got two inputs. We're going to call them 0 and 1, and another input, SEL, for select. Right, and we're going to put the variable x on there, and suppose that a goes on the 0 input and b goes on the 1 input. What this means is that if x is a 0, you send a to the output, and if x is a 1, you send b to the output. Right, so we can write that as a Boolean expression. If x is a 0, I should send out a and x because that's going to be a. But if x is a 1, I should send out b and x, right, because that's going to be b. Right, so that's what a multiplexer does. And the Shannon expansion theorem is nothing more than saying, you know, if this is the negative cofactor up here, you know, this is function f with a 0 replacing its input. And down here, this is the positive cofactor. So this is f with a 1 replacing its inputs. And the thing I'll be very careful about is that all these other inputs are the same, right? So these things and those things are the same, and those things and those things are the same inputs going there, right? This thing says, oh, look, this is just x bar and f of x equals 0 plus x and f of x equals 1, and that's just the Shannon cofactor theorem. That's just the Shannon expansion theorem. So sometimes I find that when you just look at this thing as a piece of hardware, it sometimes makes more sense for people. Now, obviously, you can do this on more than one variable, and in fact, we're going to want to do this on more than one variable. No surprise. So suppose I now have a function that's got, let's say, 4 variables, x, y, z, w, and I've already done the Shannon expansion around x, right? So this is x and f of x equals 1 plus x bar and f of x equals 0. Each of those things in the yellow box is just a function. Okay, it's just another function. There's nothing particularly interesting happening there. We could expand it again, right? So what we could say, for example, that this f of x equals 1, why don't we expand that around y, right? Well, then that's just y, and I need to cofactor it some more. So x is 1, but now y is also 1, right? Plus y bar times f of x is still 1, but y is now a 0, right? And I could do the other one as well. The negative x cofactor, f of x equals 0, if I chose to expand that around y, I'd get y and f of x stays a 0, but now y is a 1, plus y bar and f of x stays a 0, but now y is also a 0. And so this is kind of obvious. If you just take these two things in the red boxes and you substitute them back up into the yellow boxes on top, right, what you would actually get is the 4 product version of the Shannon expansion in 2 variables, right? So what you would get in this particular case is this. You would say f of x, y, z, w, that's equal to xy times f of x equals 1 and y equals 1 plus x y bar times f of x equals 1 and y equals 0. You can see the pattern here. The pattern, the variable values match the polarities on the products, plus x bar y times f of x equals 0, y equals 1, plus x bar y bar f of x equals 0, y equals 0. So when you do the Shannon expansion around one variable, you chop the function up into 2 pieces. When you do the Shannon expansion around 2 variables, you chop it up into 4 pieces, and it's just what you think. If you have the Shannon expansion around 3 variables, you chop it up into 8 pieces. You get all 8 of the products in all 8 of the polarities, and you get all 8 of the constant values, for example, x and y and z, across all of the cofactors, and you OR them all together, and you can represent the function. These things also have some notation, right? They're just also called, cofactors. It's not so easy to call them positive or negative cofactors anymore, but we just write them the same way, right? We write them as, for example, if xi is 1 and xj is 0, xi, xj bar, however you like to write it, or, right, just as I did on the previous slide, a little sloppy, but very easy to write, xi equals 1, xj equals 0. Sometimes just easier to type. And this is just the same thing as I wrote on the previous slide, xy and f of xy plus x bar y and f of x bar y plus ... for the other 4 terms. That's the 4 product version, the 4 cofactor version, the 2 variable version of the Shannon expansion. And again, I need you to remember this. Each of the cofactors is a function. It's not a number, so not like calculus here. It's a function. And if I take a function like f of xy, right, where x is a 1 and y is a 1, it's a Boolean function of all the variables that are left, but there's no x's and there's no y's in this function because they have been replaced by constants. So that's how cofactors work. Now let's go see what we can do with them.